you, Ulrika, for the introduction, and it's a great honor to be giving the first of this this new series of colloquia, and say also a pleasure to tell you something about this exciting mathematical field of geometric analysis. Let's see. Oh. So what is this subject? One perhaps rough description would be it's the application of techniques from analysis and partial differential equations to questions in primarily differential geometry, but also questions whose answers have consequences and ramifications in many other fields, including physics, algebraic geometry, and topology. And also which often these questions inspire and motivate advances back in analysis and PDE. The plan of this talk is that I'll try to convey some kind of picture of this subject through discussing 5 topics, and this will be with progressively less detail. So I won't really say anything in detail about more recent advanced things, but I will try to spend quite a lot of time on older, slightly more elementary topics where the same ideas really apply and can be explained in more elementary terms without so much technicalities. So the first topic, this is something which many of you may have encountered. It's a version of what's called the Riemann mapping theorem. So and this goes back to Riemann almost 200 years ago. We're considering a domain in the complex numbers in the plane, a bounded domain and simply connected, so no holes, not an annulus or something like that, and with a smooth boundary. Then the statement is that there's a conformal homeomorphism on this domain to the unit disk. So conformal here means that the map preserves the angles between curves meeting at a point, and also the signed angles. So we're preserving the orientation in this discussion. So I'm sure many of you have, it's quite familiar. If we write our function as in terms of its real and imaginary parts, u and v, then this conformal condition is expressed by the Cauchy-Riemann equations, written down here, first order linear partial differential equations for u and v. And these also express the fact that the function is a holomorphic function of the complex variable, x plus iy. Now this is our picture, this is our simply connected domain. The statement is that we can map it to the standard disk, preserving angles between curves meeting at a point, or in other words, by a holomorphic homeomorphism. So we want to explain how results from partial differential equations can be used to prove this important statement. So the key player here will be what's called the Laplace operator on acting on functions on the complex numbers, just the sum of the second derivatives in the 2 directions. And well, we write 2 closely related statements. They both involve solving a boundary value problem on this domain omega. So the first statement is that if we have any function on the boundary, then we can extend it over the domain to what's called a harmonic function, satisfied the Laplacian of the function is 0, with the given boundary value. The second statement is that if we have another function rho on the domain, then we can satisfy the equation Laplacian of psi is equal to rho with psi vanishing on the boundary. So these are closely related. It's easy to see that the second statement implies the first statement because we can choose any extension phi 0 of h over omega and then apply the second statement to the Laplacian of phi 0 and then use the resulting function phi to modify our original extension. On the other hand, the first statement implies the mapping theorem with a few additional arguments. So what we should recall that if we have any harmonic function, the Laplacian of the function is 0, or a simply connected region, then we can find another function such that, so the first function is p, the second one is q, we can find q so that p plus iq is holomorphic. In fact, we can define q by a path integral involving the partial derivatives of p, and the condition that this is independent of the path is precisely the Laplace equation for p. So this notation means that we fix some base point z0. For any other point z, we choose a path from z0 to z, and it's a fact that this equation, the hypothesis on p, implies that this is independent of the path chosen. So we can obviously suppose, without loss of generality, that 0 lies inside our domain. And then we have a function, just the logarithm of the modulus of z, which is harmonic, but it's harmonic on the whole plane minus the origin, where of course it has a singularity. So we'll define our function h on the boundary of omega to be this log of the modulus of z. The origin doesn't lie on the boundary, so this is a nice smooth function on the boundary. And then we apply statement 1 to obtain another function phi, and then set p is the log of modulus z minus phi. So this is harmonic, I'm sorry, this should be omega minus 0. It's harmonic on omega, but we should remove the singularity at 0. And by construction, it vanishes on the boundary because that's exactly the way we chose our function phi. So when we've removed the origin from omega, it's no longer simply connected. But if we make a cut along, for example, the negative real axis, then we get a simply connected set, U. So on this set, we can find another function, Q, so that P plus IQ is holomorphic. So this function Q has a jump as we go across the cut. If we take 2 points close to the cut on either side, the value of Q will differ by 2 pi. That means that if we take the exponential of this function, then this will be well defined, because if we change P plus IQ by adding on 2 pi I, we don't change the exponential. So this is a well-defined holomorphic function on our domain, and by construction, the modulus of this function on the boundary is equal to the exponential of the real part of P plus IQ, which is just P on the boundary, and that's 0. So it satisfies the condition that the modulus of f is 1 on the boundary. So this is then some simple extra arguments, which is the required conformal homeomorphism from our domain omega to the unit disk. This is a picture to illustrate what we've said. This is our domain. We've got the origin. We make this cut along the negative real axis here to get something simply connected. We defined, we have our function p. We define q by these path integrals, as we indicated. And then, although q has this discontinuity across the cut, when we take the exponential of p plus iq, that discontinuity disappears and we get our well-defined function. So this is just to explain how this statement about solving partial differential equations has this interesting geometric consequence about constructing conformal mappings, or if you like, holomorphic mappings. So let's now contemplate these PDE statements that we enunciated. So one gets insight into these from a variational formulation, what might be called the Dirichlet principle. So for that, we should recall a basic identity involving this Laplace operator. If we take any functions lambda and mu on our domain, where lambda vanishes on the boundary, then we can take this quantity here. We take the inner product of the derivatives of lambda and mu, given by this formula here, integrate that over omega, and then that can be expressed as the integral of lambda times the Laplacian of mu, well, with a minus sign. If we took arbitrary functions lambda and mu, we would get an extra term involving integral over the boundary, but the condition that lambda vanishes on the boundary means that is absent. So now, let's suppose, in fact, we do have a solution of phi of our problem in statement 1, of my harmonic function equal to the given function on the boundary. But let's consider any other function, phi tilde, with the same boundary value. So they differ by a function lambda, which vanishes on the boundary. And then let's compute this, the integral of the pointwise norm squared of the derivative of phi tilde. So this is, in the notation we had before, the inner product of the derivative of phi tilde with itself, of course. So that's, we just expand this out, we get 3 terms, and the identity that we wrote down before, applied with mu equals phi, is exactly what we require to show that this middle term is 0. So this integral of the square of the norm of the derivative of phi tilde squared is bigger than the thing for phi because they differ by this positive term here. So what that's saying is that the solution phi minimizes this, what's called the energy, the integral of the square of the derivative, over all functions with a given boundary value. If you like, the solution phi is the most efficient way of filling in with a function omega equal to the given h on the boundary in the sense of minimizing this energy. And of course, all this has roots in classical mathematical physics. In the construction we made above, the function p would correspond to the electric potential due to we placed a point charge at the origin, and we earth the boundary of omega, in the sense we force the potential to be 0 on the boundary of omega. So the function p we were describing corresponds to the very natural physical question. And this integral of the derivative of p squared is the energy stored in the electric field. In fact, when we mentioned this result goes back to Riemann, Riemann's proof was more or less following the lines we've indicated, a kind of a physics proof, arguing that from this characterization is clear that this function p should exist. Of course, that is not exactly a proof by the standards of rigorous mathematics, and it took quite a few years before techniques in analysis developed sufficient to turn this kind of physics argument into a completely rigorous proof. The earliest proofs of the mapping theorem went by more roundabout routes. But nowadays, and for maybe a century or so, it's perfectly possible to prove these statements that we made about solutions of these boundary value problems.
Simon, can you hear me? And there's a question, one of the people in the audience would like to see statement 1 and on the second slide again.
Go back to statement 1, yeah. Okay.
Is just for a second, maybe.
This one?
I assume that is the one. Is that the second slide? Yeah. Yep.
So this is statement 1, is that we can fill in, if we fix the function on the boundary, we can fill in with a harmonic function satisfying the Laplacian of phi is 0.
Great. And Mingyong, people will be able to access this, I guess, afterwards. So, and if you miss something, you will be able to access this afterwards as well. But thank you very much. And so says Giovanni, who asked the question.
Okay. So shall I carry on?
Yes, please.
Okay. So I want to talk about, we've talked about the kind of the motivation for solving these boundary value problems and some sort of physics background. What is the, how do we actually prove the existence of a solution to a PDE question of this kind? And we're not going to be able to give a complete proof, of course, but we can maybe indicate some of the things that go into such a proof. So the strategy, or the one we're going to indicate, is again to minimize a functional. So this is, so now we have this function rho. So we're taking the same kind of Dirichlet term involving the L2 norm of derivative, but we're adding on a term involving rho. But now we're considering this over all the functions which vanish on the boundary. So the same kind of manipulation we did before shows that if we find a minimizer, then it will satisfy the PDE that we want. So why should we be able to minimize what's called a functional on a space of functions? Of course, in a sort of a more elementary setting, if we have some compact topological space, X, and a continuous function, let's call it J, on it, then that function always has a minimum. I mean, how do we prove that? If maybe let's say it's sequentially compact to be completely precise, we can take a minimizing sequence xi of points in X such that the value of the functions j of xi tends to the infimum, which a priori could be minus infinity. Then what we know, because the space is sequentially compact, is that this sequence has a convergent subsequence. So in fact, we might as well suppose that the original sequence was convergent. And then it's easy to show that because the function is continuous, that the limit is the minimizer that we desired. So in our problem, we have a functional on a space, the space script x of all functions vanishing on the boundary of omega. But there's an obvious difficulty, an obvious difference from what we were considering before, that this space is definitely not compact. It's an infinite dimensional space, not even locally compact in any sort of reasonable sense.
Simon, before you go on, there's a question where the 1/2 comes from in the formula, I think.
Let's hope I got it right. Okay, well, let's say it's an exercise to check if the half should be there. Let me just think. Yes, I think you're right. I think the half shouldn't be there. I think that's right.
Well done, Sonia.
Yeah, that looks like a mistake. So the point is that similar ideas can be made to work in an infinite dimensional setting. And one of the key things in doing that is what's called the Poincare inequality. So that's, of course, applies much more generally, but in the case at hand, this says that if we consider all functions vanishing on the boundary, then there's what's called the L2 norm of the derivative that we were considering before controls the L2 norm of the function. So the L2 norm of the function, or the square of it, is less than some constant times the L2 norm of the derivative. So for now I'm going to use this standard notation with these denote L2 norms. Yeah. Well, this is not it's not that hard to prove, but it's a fundamental fact in analysis and PDE. So we also have the Cauchy-Schwarz inequality, which says that this inner product, the integral of rho times phi tilde, is bounded by the products of the L2 norms. So if we combine the two, we get a go back to the definition of this function in J, we can get an inequality like this. So for our minimizing sequence, this J of psi tilde I will certainly be bounded. In fact, since J of 0 is 0, we can, if we take a minimizing sequence, then J of psi tilde I could be supposed to be less than 0. So if we take this inequality, then we can cancel out, we can divide by the norm of phi tilde I, so we get a bound on the L2 norm of the elements in our minimizing sequence. But going on from that, we can use something rather stronger than the Poincare inequality to a compactness statement. So if we have this is what's called the relic theorem, or special case of a more general theorem. But if we have a sequence of functions vanishing on the boundary, where the L2 norm, okay, so there's another, I apologize, this is a rather a more serious mistake. This should be the L2 norm of the derivative of the function is less than a constant. Then it says there's a subsequence which converges in L2 norm. Yeah, so again, this should be the norm of the derivative of the functions. So this is a kind of an L2 version of what many of you may have encountered, what's called the Ascoli-Zähler theorem, which would imply that if we were just working with the supremum norm, if we have a sequence of functions where the derivative is bounded in L infinity, then there is a subsequence which converges in the C0 norm. So for our minimizing sequence, again, going back to the definition of the functional, we have a bound on the L2 norm of our functions. So that means that without loss of generality, we can suppose that our functions converge in our minimizing sequence. At least they converge in the L2 sense to some limit. And in fact, it's quite easy exercise to see that this limit is independent of the choice of minimizing sequence. So using these facts, the Poincare inequality and the relic theorem, we do get something. We get this L2 object, psi tilde, a limit of a minimizing sequence, which obviously, if there is a solution, this will be it. So the more technical work, which we won't go into, is to show that this object we've obtained, this thing which is a priori just an L2 function, is in fact a smooth function and satisfies our PDE. So let's now have an interlude in which we talk about some basic differential geometry, beginning with the classical situation of a surface in R3. And then we have distinguished two different kinds of questions, one involving what we might call the intrinsic geometry of the surface. So this involves properties that could be perceived by a fly. You think of a fly walking around on the surface, but who has no knowledge of the ambient space. So the three-dimensional space in which the surface sits. So the fly could measure the lengths of paths in the surface, and he could work out the velocity vector of a path, which would be, say, a tangent vector to the surface, that we called. He could understand the area of a region in the surface, the derivative of a function defined on the surface, and the size of the derivative at a point, and also the integrals of functions on the surface with respect to the area measure. So these are all intrinsic objects. They don't require any knowledge of how the surface sits inside the three-dimensional space. But we also have extrinsic geometry of the surface in the three-dimensional space. And the standard theory about this involves what are called the principal curvatures. So if we have a point in the surface, then we can choose an orthogonal coordinate system in the three-dimensional space adapted to the surface of that point, so that the x1 to x2 plane is the tangent plane of the surface, and the surface locally a graph. x3 is a function of x1 and x2, and we can arrange that the function is lambda1 x1 squared plus lambda2 x2 squared plus higher order terms that are smaller than x squared. These numbers, lambda1 and lambda2, are what are called the principal curvatures of the surface at the point. So these are the basic extrinsic invariants of a surface in R3. But by the famous theorem of Gauss, their product, called the Gauss curvature, lambda1 times lambda2, turns out to be an intrinsic invariant. One way of defining it intrinsically is by a formula for the area of a disk in the surface of radius r. In a sense, we take from our point, we look at all the points whose distance measured within the surface is less than r. That defines this disk dr. We work out its area, and we consider that for small r. Of course, the leading term is the same as we would have in the plane, pi r squared, but the first correction term is an r to the fourth term, which is given by this Gauss curvature up to a factor. And then, of course, we have our higher order corrections. This is a picture. This is a piece of surface with a saddle shape. The principal curvatures would have opposite sign. It's curving in different directions. That means the Gauss curvature would be negative at this point. So that's saying if we take the area of the disk, intrinsic disk in the surface, that will be somewhat more than the area of the corresponding Euclidean disk. So this intrinsic geometry can be extracted to yield the notion of an abstract two-dimensional Riemannian manifold, not necessarily just a subset of three-dimensional space. And more generally, we get the notion of a Riemannian manifold of any dimension, where points in a neighborhood, a given point, a neighborhood can be described by local coordinates, and what's called the Riemannian metric is given by a collection of functions in these coordinates, Gij, which give the inner products between the tangent vectors in the xi and xj directions. So the majority of modern differential geometry research involves structures on general manifolds, structures like Riemannian metrics or related things, rather than the geometry of a surface sitting, or higher dimensional manifold sitting inside a Euclidean space. An important driver of that development was the theory of general relativity, which of course employed similar notions to a Riemannian manifold in the context of four-dimensional space-time. So let's now, with that background, go on to talk about topic 2, which is the question of conformal deformation of a metric on a two-dimensional manifold to constant Gauss curvature. So we're considering a compact two-dimensional Riemannian manifold. So if we have any function u on the manifold, we can change the metric by multiplying it by a factor e to the 2u. And we say these things are in the same conformal class because the two metrics define the same angles between tangent vectors, but they scale lengths at a point by the factor of e to the u. Now we can define the Gauss curvature for abstract Riemannian metrics on two-dimensional manifolds, for example, using our formula in terms of the area of small disks. And then one can compute how the Gauss curvature of the two metrics compare, and we arrive, one finds this formula. There's a missing bracket here. There should be a bracket around this term. And the formula involves another Laplace operator, so delta, which is the intrinsic Laplace operator on the manifold defined by the metric G0. And there are various ways of defining this, but one is through the same kind of identity we had before, that if we take any pair of functions lambda and mu, we take the inner product of their derivative in this L2 sense, and then that can be expressed in terms of this Laplace operator applied to mu. Here we're working on a compact manifold, so there's no boundary term. So the result we want to discuss in this section is the statement that whatever G0 we take, we can always find a function u, so the Gauss curvature of this conformal metric is constant. So we're going to consider the case where the Gauss curvature of the original metric is negative, and the constant we're going to achieve is -1. It turns out this is the main case of interest. So using our formula, we have to solve a PDE for this function u on our manifold. And this is the PDE where the right-hand side row is minus the Gauss curvature of the original metric. So this is positive by our hypothesis. So again, we've got an interesting, we have a PDE to solve with a motivation from a natural question in differential geometry. But now we have a nonlinear PDE for our function u because of this exponential term. But again, this has got a variational formulation. If we define a functional by this formula here, So it's similar kind of thing we had before, but now we've got this term involving e to the 2u, then our problem is equivalent to minimizing this functional. So we can treat this with a similar strategy to what we used in the previous topic, thanks to the favorable sign of which the exponential term here enters. So if we consider what all this expression here at a given point, it involves the value of rho at this point, which is some real number. So let's consider for any given fixed number, say underline rho, positive number, we have a function e to the 2u minus underline rho times u. So the crucial thing is that this tends to infinity as u tends either to plus or minus infinity. Go to the next slide. The function will look like this. So when u is large and positive, it's this exponential term, it grows very rapidly. When u is large negative, then it grows essentially linearly because of this term here. And that means if we go back to look at our functional, there's no point in making u very large in a region because that will be bad from the point of view of this sort of algebraic part, but also tend to increase this derivative part. Similarly, there's no point in making u very negative in a region for the same reason. So what you see is, despite elementary arguments, that you can choose a minimizing sequence which are functions that are pointwise bounded by some fixed constant above and below. So then the same arguments, going back to the definition of the functional, shows that we can suppose that u, and in fact also the e to the u, converge in L2. And again, with some more technical work, can show that the limit solves the PDE. But it's important to stress that not every minimization problem has a solution. It's not as though we just say, oh, we minimize a functional and then we can solve our PDE. Absolutely not. For example, if we change the sign in the definition of our functional, then we would get, you can imagine we would get a situation where we have a competition between the derivative term and the algebraic term, where we want to making the function large at a point maybe makes the algebraic term is favorable, but maybe we tend to increase the term from the derivative. So we get competitions between different terms, roughly speaking, in our functional, and the problem of the existence of a minimum can become very subtle. But in general, I mean, complete generality, depending on what kind of problem you're considering, minimizing sequences might just sort of go off to infinity, or they might converge to some kind of object, but not a smooth object, not in the class you originally wanted to consider. You might develop singularities of some form. And understanding these kind of questions is at the heart of a lot of research in this subject of geometric analysis. So this theorem is, you might think, why is it important that we know we can choose these metrics of constant Gauss curvature? It's important because it's some easy arguments one can deduce. It's called the uniformization theorem in the case of compact Riemann surfaces. So staying with the case of Gauss curvature -1, it's a basic fact, not too hard to prove, that if you have any compact oriented Riemannian two-manifold with Gauss curvature -1, then it can be realized as a quotient of the upper half plane by an action of a discrete subgroup of this group here, acting by Mobius maps. So we mentioned Riemann surfaces. So a Riemann surface structure on a two-manifold is something very close to a Riemannian metric. It, in fact, is equivalent to having an orientation and a conformal class of metrics. So precisely what we were considering when we were considering multiplying our metric by this factor. On the other hand, these Riemann surfaces arise in many other ways, and not when one wouldn't think of as immediately connected with Riemannian geometry. For example, as complex algebraic curves defined by polynomial equations. So we could take, say, the pairs of complex numbers Z and W, a point in C2, which satisfies this polynomial equation, and this would give a Riemann surface sitting inside C2. And then there's a way to add on points at infinity to get a compact Riemann surface. And it's a fact that when this number n is at least 3, then it will have a metric of constant curvature -1. So our theorem, proved using the solubility of this PDE and some not too difficult extra arguments, implies that something given here, this algebraic curve, also arises a different way as a quotient of the upper half plane. So this is our quotient of the upper half plane, where we have some kind of fundamental domain, and we think of it gluing together the edges of that to construct the Riemann surface. On the other hand, it's the same as this curve inside C times C. And this is an extremely important fact in many areas of mathematics. There's two ways in which Riemann surfaces arise. But going back to Riemannian geometry, these ideas have huge extensions to higher dimensions, to studying the existence of special Riemannian metrics on complex algebraic varieties of any dimension. One example of this is what are called Calabi-Yau metrics, whose existence was proved by Yau in 1978 using PDE arguments. These if you like, they're higher dimensional versions of constant curvature metrics, constant Gauss curvature metrics, and these things are crucial in the area of string theory in mathematical physics. The fact that one has these special Riemannian metrics on certain complex algebraic varieties. And indeed, this is up to the present day, this is a very active research field about understanding these questions, about the existence of these kind of metrics and connections with algebraic geometry. So let's go on to our third topic. So this is, I'm going to discuss another kind of approach, common approach to these kind of PDE problems. So we say so far we talked about a sort of variational points of view, but definitely not all PDE arise naturally from variational problems. And even if they do, this kind of direct approach by trying to consider a minimizing sequence may not really work. So another important technique is what's called the continuity method, which involves embedding the equation we want to solve in a family of equations. So to give background to this, let's recall some basic fact in multivariable calculus. If we have a differentiable map from Rn to Rm, then supposing we have a point in Rn where the derivative of this map is surjective, then a theorem, some kind of inverse function theorem version of that, says that if we have any point in a neighborhood, a suitable neighborhood of the image of x0, then we can, so if we take any y in a neighborhood of f of x0, we can solve the equation f of x equals y, where x is close to x0. We might say that the behavior of the function near to x naught is modeled on the behavior of its derivative, which is a linear map. So the same kind of result applies under suitable technical hypotheses in interdimensional settings, where we replace, of course, the map F we were considering before by something defined by a partial differential operator. For example, we could take the operator that we encountered in topic 2, this operator here. So a problem we were trying to solve in topic 2 was script f of u is equal to rho for some given rho. So another approach to that problem would be to choose some one parameter family, rho t, for t in the interval, where rho 1 is the rho that you want to consider, but rho naught is something where you know there's a solution. Of course, that's easy to produce. You take an arbitrary u naught and just use this to define rho naught. So then what we do is we want to say, let's look at the subset of parameter values in naught 1 for which there is a solution to this equation. So we know that's not empty because 0 is in the set. If 1 is in this set, then we've solved our problem. So what we want to do is to prove that this set is open and closed, because then by standard fact, because the interval is connected, it follows that the set must be the whole set. Then openness follows from a result of inverse function type if the corresponding linear operators are surjective. So what we want to do is we want to do calculus in infinite dimensional space. We want to differentiate this functional f. But there's nothing really mysterious about that. So we want to consider applying this functional to u plus a small perturbation epsilon v. And then, because the one term is just linear, so we just get this here, then all we're doing is differentiating in the ordinary sense this exponential term. So the linear operator, which is the derivative of this thing here, is it maps at a point u, it maps v to the Laplacian of v plus this scalar term. So there is a very well-developed theory of linear operators over compact manifolds. So in practice, one can very often verify or show that in these kind of problems, these linear operators are surjective and therefore deduce the openness. For example, in this case, the fact that this term is positive implies by some straightforward theory that this linear operator is invertible. But then the other side of the coin is to prove closedness of our set, and that means we have to establish what are called a priori bounds on the solution. If we can, at this point we don't maybe know that solutions exist, but what we say is supposing for some parameter value the solution exists, can we get bounds on its derivative? Can we get bounds on some kind of norm of the solution? If we can do that, then we can show that if we take a sequence of such parameter values, then we can take a limit of the corresponding solutions and therefore hope to show that that limit gives a solution for the limiting parameter value, therefore establishing the closedness of T. So the real work comes down to something quite similar to what we discussed in these variational questions. It comes down to establishing in some way bounds on the solutions. Even if you don't know they exist, what are called a priori bounds. Supposing there was a solution, can you say information about it? So a famous example of this continuity method was a result proved by both by Nierenberg and Popog-Roloff independently, is answering a problem proposed by Weil, on which Weil had done some preliminary work. And this is a very natural question about the relation, sort of in classical differential geometry, between intrinsic and extrinsic structures. So it says if we take a Riemannian metric on the two-sphere, abstract Riemannian metric, with strictly positive Gauss curvature, then that can be obtained by a suitable embedding of the two-sphere in R3. This is what's called an isometric embedding of the two-sphere with this metric into R3. And in fact, the fact that the Gauss curvature is positive means it'll be the boundary of a convex domain in R3. So something like a rugby ball or something, the boundary of a rugby ball. So it's saying that although in general there's a distinction between the Riemannian two-dimensional Riemann methods, which can arise in the classical way as surfaces in R3, and the more general class of abstract Riemannian surfaces, in the case of positive Gauss curvature, those end up being the same. But in fact, this embedding is unique up to rigid motions of R3. So the strategy of Nierenberg's proof is, the first one shows that the set of metrics with positive Gauss curvature is connected. So we can take a path from our from the metric we want to consider, G, to the standard metric, which G0, which of course the standard metric just of the ordinary two-sphere sitting inside R3. So let's have a path of metrics with positive Gauss curvature, I want to say. So then, following the same sort of procedure as considered before, we can consider the set of parameter values for which there is an isometric embedding. And we want to show that this is open and closed. So openness is established by studying the linearized problem in the same kind of spirit of what we said. And closedness requires a priori estimates or bounds on the solutions. And the key such bound, which in fact goes back to Weil's work on this question, is on the mean curvature of the solution. So this is just, rather than taking the product of the principal curvatures, we take their sum. This gives what's called the mean curvature. So we can suppose, we can choose our signs so that λ1 and λ2 are positive. So the mean curvature is a positive. So if we're supposed to know that we know the metric that determines the Gauss curvature, the product. So if we have a bound on the mean curvature, that gives a bound on both λ1 and λ2. So this is, we're not going to explain this in detail, but it illustrates an important general technique. But this estimate is obtained using the maximum principle. If you do somewhat involved differential geometric calculations, give you a formula relating H and K in the case where we do have an embedding of our surface. And this formula is that we take a certain second order differential operator, L, and apply it to H, and that's equal to the Laplacian of K plus, well, something I don't need to explain because the point is that this is positive. It's the norm of something squared. And then this term here, again involving H. So what is this operator L? If we go to a point and then take standard coordinates adapted to that point, so we take the coordinate directions x1 and x2 corresponding to the principal axes, as we described before, then at that point L is given by taking something like the Laplace operator, but we weight the second derivatives by the λ2 and λ1. The sort of sort of subtlety is that you're interchanging 1 and 2 here. This is what turns out to be the right thing. In any case, the details don't really matter in a sense. The point is that at a point where h is maximal, because of the nature of this operator, the general nature implies that L of h is less than or equal to 0, because at a maximum, the first derivatives of h must be 0, and the second derivatives must be at least non-positive. Lambda 1 and lambda 2 are positive. So, going back to our formula, L of h is negative. This term here is something positive. The Laplacian of k is just, it's some known function on our, it's determined by the metric, so it's some known function on our surface. So we get an inequality of this form. And then, of course, the crucial thing is, again, the sign here. If we had the opposite sign, then this would not tell us anything useful. But because we have the good sign here, this inequality gives a bound on h at this point, which is the maximum at the value of h, in terms of things that we know. So this is a typical example of how such an a priori estimate can be proved using the maximum principle and some rather formidable differential geometric calculations. So note, this is a global fact, this bound on h in terms of k. Locally, we don't have anything like this. We could take a piece of surface like this, where we could make the principal curvature in this direction very large. That would make h large. Provided we make the curvature in this direction correspondingly small, we can keep k to be bounded. So locally, we don't have any kind of relation like this, but maybe you could see geometrically, if we make the curvature this direction very small, then to close up, to make a closed surface, we need to consider a very, very large sort of disk-like object. So we make the area very large. So that might be a more intuitive way to think about this estimate. So my time is up. I'll finish there. I did have a couple of other topics, but what I've tried to explain how some basic techniques in this area of geometric analysis are used to prove the existence of solutions to PDE, which have interest for differential geometric problems, and often these the results extend into other areas, such as connections with algebraic geometry. I haven't managed to get to really connections with topology, unfortunately. So although everything we've talked about has been comparatively elementary, of course, and current research involves much more technically complex things, many of the ideas we've encountered are the same kind of fundamental ideas employed in current research in this area. So thank you for your attention. I'll stop at this point.
Well, thank you very much for a very